All right, guys. This is the dynamics of rigid bodies, rectilinear kinematics, our lecture one problem sets, and we'll get to go over your solutions for this. Probably most of you have already found the solution here, but hopefully you did still try to solve it and understand the relationship between displacement, velocity, and acceleration with respect to time. All right, let's get over it. So here are the problems, and we'll go with it one by one. First things first, we have here a F12-1. Okay, initially the car travels along a straight road with a speed of 35 meters per second. If the brakes are applied, the speed of the car is reduced to 10 meters per second in 15 seconds. So, determine the constant deceleration of the car. So, we have a lot of clues here. A, we're being required to find the constant constant deceleration of the car. We're already given an initial speed of 35 meters per second and a final one of 10 meters per second with a total time of 15 seconds. So if we're going to write that up, it's going to look somewhat like this. Okay. So the next up here is, of course, we're here to find the deceleration. And by deceleration, meaning it's going to be negative. So given the variables available, we could use this particular formula to solve for our deceleration. So Vf, final velocity, is equals to initial velocity plus the product of acceleration and time. So substituting the values here and probably rearranging the equation first, we can now find A is equals to Vf minus Vi, and substituting all the values should yield you negative 1.6667 meters per second squared, or simply negative 1.67 meters per second squared. Okay, so that is easy. And hopefully, if you are having trouble understanding that, you could still pause the video, rewind, and just hold it over again and go over our concepts. Okay, let's go for our next problem. Here we have a ball is thrown vertically upward with a speed of 15 meters per second. Determine the time of flight when it returns to its original position. Oh, interesting. So we have an initial velocity of 15 meters per second. We have initial speed of 15 meters per second here. All right, so our VI is known. And we're here to know the total time of flight from the moment it left your hand. I'm showing from your hand, and it returns to its original position. So this gives us several clues of its initial and final position. So the initial and final position here will return to its original. The final position will return to its original position, which is s equals to 0, basically. So our initial position and final position will be at 0 meters. All right. So in that case, we're gonna put it this way. There we go. And then we're here to find the total flight. So in this case, given our formula, we have we can use this particular equation. If you recall, the final position equals to initial position plus initial velocity times time plus at squared over 2. Luckily, this is thrown upwards, so we are under the presence of constant acceleration. In this case, the acceleration due to gravity. Now we just replace the initial and final position with 0. And now we can rewrite our equation just like so. We are now left with VIT plus AT squared. Again, further rearranging the equation, we will have something like this. Our time t here will be cancelled, so this one will be AT. And then isolating t will give you negative 2 VIA, where A is negative 9.8067 meters per second squared. Don't forget to do your unit analysis. And the total time will be 3.0591 seconds, or 3.06 seconds. That will be the total time of flight for this particular problem. Okay, let's move forward. Okay, now we have a horizontal type of kinematic problem. So here a particle travels along a straight line with an acceleration of a equals to 10 minus 0.2 seconds. So we're given an equation of a line for acceleration. So here 10 minus 0.2 seconds, 10 minus 0.2 s meters per second squared, where s is measured in meters. Now, determine the velocity of the particle when s is 10 meters. So we're here to find the final velocity or at position of 10 meters, when position is 10 meters. And we're given the initial state when the position is 0, the initial velocity here will be 5 meters per second. Okay, so how do we solve this? So let's just write down first our given. So we know that it's 10 minus 0.2 seconds. So given from the problem and the diagram provided, we know it's a constant. It's going on a straight line. So it's represented by a line. Okay, so we're here to determine the final velocity at 10 meters. So here we're going to recall that the velocity is the change in position with respect to time, and acceleration is the change in velocity with respect to time. So all we have to do now here is, given our variables, we don't have much time dito. So we're here to equate them into change in time. So we will rewrite the equation just like so. V dv equals to ADS. And we will integrate both sides of the equation. Just like so. Okay, so here, after we integrate, we will have Vf squared minus Vi squared over 2 equals to 10s minus 0.2 s squared over 2. So we're here to determine... So luckily, we're here to find Vf squared here. So that's good. We have already Vi here at s is equals to 0. All right, so all we have to do now is just substitute the equations here and isolate the final velocity, just like so. And already substituted at s equals to at 10 meters. So there we go. Okay, and then we will get the answer at 14.3178 meters per second, or simply 14.32 meters per second. Okay, next up. Oh, yeah, sorry about that. So next up is here, we have a sphere that is fired downwards. So it's quite the opposite of the previous problem. So earlier we threw it upward straight, and now we're throwing it downward with an initial speed of 27 meters per second. We're also given an equation of a line. So the deceleration is represented as a equals to negative 60 meters per second squared, where t here is in seconds. So determine the distance traveled before it stops. So for this, we just have to write down first our given. We know that our initial speed is 27 meters per second. We know that a is negative 60 meters per second squared, where t is seconds. So we're here to determine the total distance or traveled. Okay, in this regard, recall again the equations, a dv dt, or the change in velocity with respect to time, and velocity is change in position with respect to time. In this case, we're going to use dv. We need to find the change in velocity here so that we can determine our total distance traveled here. So we're going to use the acceleration formula here, and we're going to integrate them just like so. And here, just to simplify, and then the results here will be, there we go. So we assume here that the final velocity will be 0 because, it's going to stop anyway. And then simplifying further, we will get the total time here at t is equals to 3 seconds. Now that we know our time here, we can now get our total distance traveled. So we're going to use for s. We simply have to integrate on both sides. So now that we know the total time, all we have to do now here is just integrate what v here. So we understand that v here is 27 minus 32 squared. So we just integrate that. Okay. There we go. I think I made a typo here. There's not supposed to be a 2 here. So yeah. So there's not supposed a 2 there. So my bad. Okay. And then the answer will be 54 meters. So let me just correct that one bit. I think this is slide F12-6. So there we go. And so let me just erase that number 2 there. There we go. Okay, let's go back. Okay, so anyway, I already corrected that. So let's go ahead with the next problem. Okay, here we have a particle moving along a straight line such that the acceleration is a equals to 4t squared minus 2 meters per second, is where t is in seconds. When t is equals to 0, the particle is located 2 meters to the left of the origin. That gives you a lot of clues there. When t is equals to 2 seconds, it is 20 meters to the left again of the origin. So determine the final position of the particle when t is equals to 4 seconds. So the indication where the position is going to the left, which means our initial positions here at t0 and positions here at 2 seconds is going to be negative 2 meters and negative 20 meters respectively. So let's just write them down. There we go. So we're here to find the final position at t equals to 4 seconds. So all we have to do here is recall this equation. That the velocity is the change in position with respect to time, and the acceleration is the change in velocity with respect to time. All we have to do is first we gonna get v, so that we have our equation. So we're just gonna integrate that. Your usual integration. So this is integration with no limits. And then we're going to go with S, integrate that. There you go. And now here we're just going to time it down. So when t is equals to 0, S is equals to negative 2 meters, giving C2 equals to negative 2. And then when t is equals to 2, S is equals to negative 20, well, C1 is equals to negative 9.67. And then t is equals to 4 seconds, that will give us S is equals to 28.65 meters. I think there's a typo lang dito. Okay? Yeah, there's a typo lang. Dapat C1 lang to. All right, there we go. All right. We have a few more problems here. We have erratic motions naman. So a combination of both horizontal and vertical, but that's more on later on curvilinear kinematics. But here we're gonna focus on graphs first. Okay, so what if you're given a graph and then you're here being asked to solve the position and time graph and acceleration and time graph? So here we're given that S is equals to 0 when t is equals to 0. We have an equation of the line that is v equals to 2t. So all we have to do here first, okay, you write it down first, and then we going to solve it one by one. So if we first go with v equals to ds over dt to know the st graph. So in this case, we are given v is equals to 2t here. So all we have to do is just get, we are integrating both sides here to get the ds. So there we go. And then here, ss is equals to t squared. We're already given s is equals to 0. So when we integrate this, it's going to be s, and we substitute sf here. That's good. So we have our first equation, sf equals to t squared. Next up is we need to get the graph. So it's going to look something like this. So t squared. So you can assign arbitrary values. So when t is equals to 0, s equals to 0. That's correct. When t is equals to 1, should be that our sf is equals to 1. And then when t is equals to 2, that will be 4. So there we go. Now for accelerations, we have dv over dt. So all we have to do is just substitute dv. So we get the derivative of this. So we will get 2. So it's going to be a constant acceleration of 2 meters per second squared. There we go. I don't think there should be a border. It should be tuloy-tuloy lang to, though. Okay. All right. Next is the erratic motion. The problem travels along a straight track such that its position is described by ST graph. Construct the VT graph for the same interval. So we're given two states here. S is equals to 0.5 t cubed and S is equals to 108. So clearly here, okay, it's going to be constant. So all we have to do is just write down first our given and now solve for our VT graph. We will solve for V equals to ds over dt. So let's solve for S is equals to 0.5 t cubed first. From 0 to 6. And then we will have this. Our answer is V equals to 1.5 t squared from the graph. So we can predict our values here and plot them out later. So our t is equals to 0, v is 0. Our t, when t is equals to 1, that will be equals to 1.5. When t is equals to 6, that will be 54. Now from 6 seconds to 10 seconds, it's somewhere going to be like this. So it's going to be 0 here, since we have already a clue that our velocity will here be 0 because our position remains the same. Okay, so our total graph would look something like this. So after from 0 to 6, it's going to climb up to 54 meters per second. And after achieving, and they have to hold the same position so that from 6 to 10 seconds, our velocity will simply drop to 0. Next up, we have a dragster here. So the dragster starts from rest and has a velocity described by the graph, and construct the ST graph during the time interval of 0 to 15 seconds. We here also determine the total distance traveled during the time. Judging from the graph, you can already determine the total distance by getting the area under the curve. So we have two triangles here. We simply have to get the area under the curve here if you're familiar with that. But I think I did the long version here. So again, we have two states here. So let's solve one by one from 0 to 5 seconds first. So recall again our equation, V equals to ds over dt, and remember that the change in position is also final minus initial position, which is also equal to V dt by manipulating the formula. Okay, after that, from 0 to 5 seconds, all we have to do is to integrate both sides of the equation. So that will be ds equals to 30t dt with its respective limits. There we go. And upon simplifying, our SF would be 15t squared. So at t equals to 5 seconds, 0 to 5, that will be 375 meters. So we solve the total distance travel from 0 to 5 meters. Okay, next up is the 5 to 15. So here, our 375 will be our initial position, and our time here, 5 seconds, will be our initial time. So substituting the equation of the line here using the same formula, so that will be negative 15t plus 225, and we will try with something like this. I did the longer version here. You will get along the lines of the final position is equals to, at 5 to 15 seconds, equals to negative 7.5t squared plus 225t minus 562.5. And all you have to do here is just substitute the 15 seconds, and you will have 125 meters. There you go. Last but not the least, the graph. The graph will probably look something like this. All right. There you have it. If you have any further questions, you can approach me during class, and or you can review this this recording. So thank you so much.